we will work on an example. Now, let's see what happens with the warm-up, meaning the Dr. Pepper and the ice. Now, this should say 25 grams, so let's correct it. Just a marker, white marker. And we'll make that into a number 5. That's weird. Let's try it again. There you go. So 25 grams of ice at 0 degrees are used to cool a warm Dr. Pepper, which is in a 490 milliliter, that's about 16 ounces, cup. What is the final temperature of the drink? Assume the Dr. Pepper is at room temperature, about 25 degrees, and treat the drink as water. Don't forget, every time we have assume in physics, that's good news. And we are given the latent heat of fusion of water, that is 334 joules per gram. Notice that we have grams, thus we don't have to convert the grams into kilograms. However, we should also be careful about our value for specific heat, okay? And you'll see why the fact that we can treat the Dr. Pepper as water is super important. But you'll see why. So let's start defining what's happening before we start, because we normally start with the given, but I want you to really understand what's going on here. So in this case, we have to use energy conservation, latent heat, and specific heat. So we know that because of energy conservation, that was my bad, energy conservation, we're going to have, or we need to account on the ice, right, for the energy required to have that phase change and to have a change in temperature. So that energy required to have a phase change plus a change in temperature should be equal to the change in temperature of the Dr. Pepper, meaning on the right side, we only have to account for a change in temperature, okay? And that's using the specific heat capacity equation. On the left side, we're going to have 2 parts. On the right side, only 1 part. Okay, so that's the most important thing. That's the mistake, I guess, number 1 mistake the students make, which is only accounting for the change in temperature. Okay, so now let's write down our given. Okay, given. So we have mass 1. That'll be 25 grams. So anything with the subscript 1 will be related to the water. I'm sorry, the ice. The ice is water, right? And then, so that means temperature 1 initial is 0 degrees Celsius. Then mass 2, which is the mass of the Dr. Pepper, we don't have the mass in grams. However, since we are treating the drink as water, that is the Dr. Pepper as water, because of the density, we can say that the mass of the Dr. Pepper is 490 grams. I told you it was going to be super useful. And the temperature initial of the Dr. Pepper is room temperature. In this case, we say is 25 degrees Celsius. And then we have I'm going to write the specific heat first. Specific heat of water. Now, I'm not going to add the W here. Well, I mean, just for the given, yes, but for the equation, no. Because it's the same for both, because ice is frozen water, and we're treating the Dr. Pepper as liquid water. And the value is 4.18 joules per gram times degrees Celsius. This number is due to the fact that I have grams. Okay, so be very careful with that. Then we have the latent heat of fusion, which is 334 joules per gram. If you go to the book, you'll find kilojoules per kilograms. So since we're using joules and grams, essentially the same. And we're trying to find the final temperature of the drink after the ice has melted completely. Why? Because it makes the math easier. I know it's going to be watered down Dr. Pepper, but it's going to make the math easier. Okay, so don't forget, on the left side, pertaining to the ice, we're going to have two parts. On the right side, only one part. So first, let's account for the change of phase. So we're going to have Q1, that's the ice. The energy that it's going to be, I don't want to say recede, but added to the ice will be the same as the energy released by the Dr. Pepper. Q1 equals Q2. In this case, Q1 will have two parts, right? Will be the change of phase, so mass 1 times latent heat of fusion plus mass 1 specific heat times the change in temperature 1. That will be equal to mass 2 times specific heat times the change in temperature 2. Okay, before we continue, we have to make a statement over here. We know that the temperature final of the drink will be greater than the temperature 1 initial, right? Because it's 0, so it's going to be greater. Of course, the 25 grams of ice at 0 will not make the 490 grams of Dr. Pepper to be at 0 degrees. And we know that the temperature 2 initial, that is the 25 degrees Celsius, are greater than what the final temperature is expected to be. Of course, because the Dr. Pepper is going to give energy, transfer energy to the ice, and that's why its temperature initial will be higher than the final temperature of the drink, which is the main idea, right? The whole goal, to make this colder. All right. Based on that, we can have the our change in temperature, meaning we're going to know which one minus which one we should have. What that means is this. So mass 1 times latent heat of fusion plus mass 1 times specific heat, parentheses, temperature final, minus temperature 1 initial, equals mass 2, specific heat, parentheses, temperature 2 initial, minus temperature final. Guys, from here is just algebra, so if you understand this part, everything we've done, that's the physics. Of course, math is very important. You need to know your algebra. The rest is algebra. But the physics, in a way, end here, right? Knowing what's happening, energy conservation, heat required. And now let's do some algebra. The first thing to notice, and I chose 0 degrees. I mean, that's a common number for ice. I could have said with salt, right, it'll be like 1, 2 degrees. But then I would not be able to do this. I'm going to cancel temperature 1 initial because it's 0, right? It's 0. Even to multiply mass 1 times specific heat times 0, I'll get 0. Lucky us. So mass 1 times latent heat of fusion plus mass 1 specific heat temperature final equals mass 2 specific heat temperature 2 initial minus temperature final. Now the whole idea is we have to solve for temperature final. So I'm going to get rid of this parentheses and then try to solve for temperature final. So it'll read mass 1, latent heat of fusion, plus mass 1, specific heat, final temperature equals mass 2, specific heat, temperature 2 initial, minus mass 2, specific heat, temperature final. I'm going to move this term with the temperature final to the left, in this term with the latent heat to the right. So plus mass 2, specific heat, temperature final, so that it cancels. I'm going to write it down over here, plus mass 2, specific heat, temperature final. And then let's move this latent heat minus mass 1 times latent heat of fusion minus, oh wait, so this cancels. So it'll be minus mass 1 latent heat of fusion. There you go. So we'll have mass 1 specific heat, temperature final, plus mass 2 specific heat, temperature final equals mass 2 times specific heat, temperature 2 initial, minus mass 1 latent heat of fusion. Alright, now I'm going to factor out temperature final and specific heat. You'll see why, okay? So I'll have specific heat times temperature final, parentheses, mass 1 plus mass 2 equals, now, I don't have specific heat in this one, right? So I cannot factor out anything per se, but I can do, I don't want to say a trick, but something so that I can have this as if I had factored this out and have my equation to be mathematically sound. So if I were to write C and then parentheses, I'll have mass 2, temperature 2 initial. Since I don't have anything here, I'll do minus mass 1, oh, sorry, well, 1 over specific heat times mass 1 times latent heat of fusion. Alright, so now I can cancel the specific heat here and here, and it's still going to be correct because I have this term. So now I have temperature final, let's try it again, temperature final, whoops, parentheses, mass 1 plus mass 2 equals mass 2, temperature 2 initial, minus, so I'm going to write it like this, mass 1 times latent heat of fusion divided by specific heat. Let's do a parentheses here. Oh. One more time. Let's try one more time. I can do this. There you go. That's a little bit better. And now, let's solve for temperature final. So I'm going to divide mass 1 plus mass 2. This cancels. And I have my equation for temperature final. This is going to be challenging for the parentheses and brackets. So let's see. Mass 2, temperature 2 initial, minus, I'm going to do the parentheses after this. Mass 1 times latent heat of fusion divided by, let's try that again, specific heat divided by mass 1 plus mass 2. Now, all we got to do is substitute. Let's go look at our given. Well, I didn't state that this is the mass for the Dr. Pepper, but now you know. So let's substitute those numbers. So then let me do it with blue. Just change it up a little bit. Temperature final equals mass 2, that is the mass of the Dr. Pepper. So we'll have 490 grams times temperature to initial, that is the temperature initial of the Dr. Pepper, which was 25 degrees Celsius, minus, now we're going to have brackets, I'm going to add them at the end, mass 1, that is the mass of the ice, 25.0 grams, there you go, times the latent heat of fusion of water, 134 joules per gram. Now what I want to point out is if we were doing the opposite, meaning freezing, we would need to account for a negative sign here, okay? And then that's divided. I'm not even going to try. I'm just going to make use of my OneNote. Times the specific heat, which was 4.18 joules per gram times degrees Celsius. And then we're going to add brackets to this. Let's fix the right side. I guess. And all that divided by mass 1 plus mass 2, which is mass 1, that is the mass of the ice, 25.0 grams, plus 490 grams. Okay, we're ready. I'm going to have a lot of parentheses, so let's do parentheses, and then 490 times 25 minus, now I'm going to need double parentheses because it's 25 times 334 close parentheses divided by 4.18. There you go. I add an extra parentheses, which is okay. And then that'll be divided by 25 plus 490. So 19.91. Two significant digits. Let's leave it at 19.9 degrees. So the answer is we should get more ice. Well, I'm kidding. The answer is 19 degrees, almost 20. So that's not very cold. Huh. So I guess we should get more ice, huh? So 19.9 is our final temperature. So T final, 19.9 degrees Celsius. And there you go. That is it.